the session there. Um, yeah, I think it's 5 minutes past, so we can probably get started. Hey everyone, just to start again with a quick intro of myself. My name's Karan. I'm currently working as a data scientist, and the agenda for this session was to sort of start a casual hangout of sorts around talking around research papers that we all may find interesting or sort of relevant in this day and age. Um, this session, we'd be going over the LlaMa paper. I'd linked it as part of the description of the event. Hopefully, folks had a chance to look through it. Um, and yeah, maybe let's get started. I'm just quickly pulling up the slides. My bad, folks are still joining. Let me just quickly move this out of the way. Awesome. Let me know if you guys can see my screen and everything's working fine. I'll just quickly sort of set sort of like meeting guidelines, I guess. Again, awesome. Seems visible. So yeah, meeting guidelines. The idea is to have like a quick overview of the paper. Maybe like spend 20 to 30 minutes discussing sort of like the highlights of the paper, and then go into a quick Q&A around the paper mainly. It's less of a Q&A around what LLMs is as it is right now, but rather what LLM space looked like as it was in 2023 when the initial LlaMa paper came out. In terms of Q&A, you guys can drop your questions on this Excel. And again, whenever I read a paper, I sort of create a set of notes, and that set of notes will be available to folks who actually ask questions. This is just to incentivize people to ask questions. Again, I may not know all the answers, but what I found in my experience is just having a group of folks who sort of read through the paper and ask questions, no matter how out of the field they are, just ask questions to each other and try and explore the space more together. That will help you enrich your understanding of that particular space. So irrespective of the size of the group, as long as we have a group of people who are willing to ask questions, I think the session will be extremely fruitful, not just for me, but for everyone on the call as well. So feel free to drop your questions on the Excel, and to folks who do drop questions, I'll be sending out my notes, which sort of I made on this paper as well, which I think would sort of give a high level idea about the paper, plus dive deep into certain implementation side concepts that's used in the paper. Cool. Starting with the agenda, we'll go over a quick sort of intro of how to read papers. Probably we'll only be doing this for the initial maybe a few more people joined, 2 or 3 calls that we have. Just because like I feel like at least when I started out, I didn't approach reading papers the way I should have. So we'll start with a quick intro of how exactly to read papers, and then we'll go into the sort of like the phased approach of analyzing a paper, starting with what the problem and the proposed solution is, what the LLM space looked like in 2023, the research space, what it looked like, and how this particular paper proposed to add value, the approach and the results that this paper sort of discusses, my perspective on the paper, my perspective on their results, and then we'll dive into the discussion section where hopefully we'll have like some questions, and we'll try to get them answered again as a group. The idea is sort of just to have a casual hangout where all of us sort of ask questions, and it's less sort of speaker to participant sort of functionality, but rather just a group of people trying to understand the research in the space. So yeah, starting with how to read papers. So this is something that I picked up when I was doing my master's. My prof said that don't try and understand the paper in one go, rather use what we call a phased approach. Now, for folks who are interested in getting a bit better understanding of the phased approach, I did link a doc on sort of like that you can download for free on our TopMate, which you can use to sort of understand papers. So do check that doc out. It provides a bit more details around how to approach this phased reading, and sort of questions you can ask at each point of the phase to make sure that you are on the right track with the paper, or if this is a paper you should continue to read or not. So initially, the phased approach starts out by you just reading the intro and maybe the conclusion section, the abstract intro and conclusion, just to understand what the problem this paper is tackling and what the proposed solution this paper is presenting is. And this is actually a good point to sort of figure out whether this paper was actually relevant to you, whether you resonate with what the work that's being done in the paper is. And if you don't, feel free to sort of drop this paper then and there. You don't need to read every paper just because like somebody else recommended it, or just because it's popping up on your feed. If it's something that resonates with you, go ahead. And this point where you read the abstract, introduction, conclusion, that's a good point to make that call. Next is to understand the research space. So like I said, when you use this phased approach, you don't need to run through all these phases in one day. Usually, like I spend a Sunday skimming through a few papers and picking out one, sort of like maybe 2 or 3 papers that I would like to read over the next week. So this one happens on one day. Then understanding the research space happens maybe on across 2 days. So I take a paper, I sort of read through their prior work or related work, or sort of like previous work that sort of cited in the paper, and try and understand how they build on previous research, because more often than not, most work isn't truly extremely novel. It builds on prior work in some way, shape, or form. And if you see a lot of citations in the prior work, and if you see sort of a clear story coming out in that related work section, that's typically a good indication of a good paper. And again, it's sort of important to understand the space around that particular work to help assess the value of this particular paper. So don't skip out on reading the prior work. Take maybe a day or two, use Google, or nowadays use ChatGPT, whatever you need to try and understand some of the prior work. You don't need to necessarily go out and read the other papers. You can definitely use ChatGPT to get summaries, or just read the intros to other paper. Don't go into this habit of, just because this paper is citing an earlier paper, I have to understand that paper, so I need to read it thoroughly. Don't do that. You get into a depth first search of reading papers where you don't actually end up reading a lot of relevant work. So don't do that. Just stick to the intro and conclusion if when it comes to the prior work related papers, and definitely use ChatGPT or Claude for summarization, so that you can move through related work quickly. But typically, again, that's another part of the phased approach. You take maybe 2 days. So usually I do Monday and Tuesday for understanding the research space. Then once you understand space, then that's when you can actually start to understand how this particular paper that you're reading, for instance, if you're reading the LlaMa paper, how did LlaMa actually approach adding value to the space? What was their approach, and what kind of results did they get? So this is primarily the technical portion of understanding a paper, where you try to understand what models they're using, what methods they're using, and try and figure out why they made the design decisions they're making. So in this paper, you'll actually see quite a few sort of changes they're making to the transformer architecture, like Swig-Glue and RMS normalization, a few things like that. So, and a good indication of a good paper, which this paper does have, is whenever they're making those design decisions, they cite previous work where it has sort of worked out, and a reasoning for using that. So that's a very good indication of a good paper. Like especially if folks on the call have actually had the opportunity to write a paper, you will, when you work with your prof will always call out the fact that, okay, you didn't cite why you mentioned this, you didn't cite why you're saying this, you didn't cite why you're using this method. Like getting those citations right and figuring out why you're making the decisions you're making, and basing it on actual prior work is quite important, and it's a good sign of a good paper as well. So again, when you read through the approach and results, if you feel like they're not really describing their method in a detailed manner or in a manner that you might be able to do down the line, it's also a sign that, okay, this might not be a paper that might add a lot of value to me, so I can drop this paper here. So at the start, where you try to understand the problem and solution, and towards the middle, where you're trying to understand the approach and results, in either of those places, if you feel like this paper won't add a lot of value, drop the paper then and there. You don't need to read all the papers out there, and you don't need to stick with reading a paper just because you started it. Just letting a few more people in. Hey, welcome. We just started with sort of like how we go about reading papers, and I'm just walking through the phased approach. The guide is available on TopMate for you guys to download for free as well. I'll actually drop the link to the guide just in case folks don't have it. Good. Yeah, so we were at understanding the approach and results section of the paper. Once we have a decent idea about what their methods and models were and how they actually approached developing whatever that proposed solution was, then we come into critically analyzing that particular paper. So this section where you try to understand if they're using benchmark datasets, are they using benchmark evaluations, and are their methods sort of truly novel, or are their methods sort of building upon what existed earlier? So again, this is a good point where if you feel like they aren't really using the benchmark datasets that's there in the field, or if they're using some kind of niche evaluation metrics to showcase some other kind of improvement to the model rather than improvement on some of the mainstream metrics, it could be a paper you might want to be a bit wary of. And how you understand whether it's a benchmark dataset or benchmark evaluation metrics is when you go through the research space, you'll sort of get an idea about what the benchmark datasets are and what the benchmark evaluation metrics are as well. So this is a point where you sort of, I would say, even like nitpick to a certain extent what the paper is sort of proposing. Just a quick call out, folks, do mute yourself if you're not already on mute. And the last section, sort of discussion with your peers. Like I mentioned, you just need a very small group of people who actually read papers and are willing to ask questions no matter how far out of field they are. As long as there is some conversation around latest work within your group, you will sort of understand that latest work better, and you'll be able to even implement and be motivated to implement the latest work better as well. So with this group, that's what I'm hoping to achieve. As long as we as a group are willing to ask questions around research, we'll be able to learn more and more. Cool. Now, sort of like starting out with the paper directly, like I mentioned, we started the phased approach. Initially, we try and understand what the problem and the solution is. So for the LlaMa, what the paper states that their solution is that they were trying to build a set of foundational models for research. And the sort of main takeaway that they're giving is that they were able to showcase that they can build models that are significantly smaller. They say around 5 to 10x smaller than what the SOTA models at that time were, which they called out as Palm, Chinchilla, OPT, Bloom, a few other models. So compared to those large language models, they could build models, essentially the LlaMa model, which is 5 to 10x smaller, but gave better performance. And they were trying to convey this theme that you don't need to necessarily keep on scaling the models over and over again. If you scale your data set and maintain a good quality data set, you can also get a decent amount of performance. This wasn't, we'll see that later on, this wasn't necessarily novel. There were other LLMs that actually did it. Just admitting a few more people. Cool. So there were other LLMs that also actually try to convey this message. But sort of a key takeaway from LlaMa was that they were able to use completely proprietary they were able to use completely publicly available data sets and not depend upon any proprietary data sets, which like other LLMs thus far seem to be using. So they use completely publicly available data sets, and therefore anybody could sort of use it going forward to a certain extent as well. And yeah, they showcased that this smaller model was able to achieve better performance on a lot of language tasks. Not all, there are some places that it falls short, and we'll see later on in the paper that one of maybe the shortcomings of this paper is sort of on the explainability part. They don't really explain why the LlaMa model is falling short in certain cases. They do cover that to a certain extent in the next papers like LlaMa 2 and the latest one. So yeah, the two takeaways: the model is significantly smaller than what is SOTA, yet the performance is better. They trained it completely on open source data sets and not necessarily, and didn't use any proprietary data sets, which is pretty cool that you could achieve that. Looking through comments, papers with code quite very well helps in finding the metrics which are common for any particular task, and also overall landscape for any task. Papers with code does have like really good sort of like these leaderboard representations as well, which is really cool and helpful in understanding what the metrics look like across certain data sets. So yeah, that's a really good call out, Krishna. Just admitting a few more people. Cool. Now, coming into sort of the research space, again, the pictorial representation to the right sort of represents all LLMs, even the LLMs till 2024. We won't be necessarily diving deep into the LLMs of 2024 because the paper came out in Feb 2023. But it's good to get like a mental map of the space before you dive deep into the paper. And I just want to share my mental map for folks who have read the paper. Feel free to share your mental maps on chat as well. So my mental map that I'm using, sort of like a high level one, language models have been around for a while. The idea was to, the key idea that they sort of narrowed down on, or the key idea that they were able to perform well on, was sort of next word or next token prediction, essentially. Initially, it started out as sort of n-gram statistics based models, but then slowly deep learning came into the picture, and they were able to use models such as RNNs, LSTMs, and eventually the transformer architecture that most of us know and love. It sort of reached that space where transformer became kind of the SOTA, and people realized that scaling the transformers, essentially using sort of like stacking transformers one on top of the other, was able to improve performance to a certain extent. And that's where sort of the architecture evolution, I would say, kind of plateaued, and people started developing what was called these scaling laws. Essentially, the gist of the scaling laws is that you can increase your model size and get better performance. You can increase your data set size and get better performance. And if you have more compute, you can increase your performance as well. The problem was, if you increase any of them singularly, like model size by itself, if you increase singularly, you'll reach a point of diminishing returns, where after that point, you have to increase your compute or your data set size to keep on getting better and better performance. So there were these scaling laws that were established for a while. And then in 2022, a researcher called Hoffman came in and sort of I wouldn't say drastically revolutionized, but kind of altered the how we perceive those scaling laws, primarily by stating that um, how much performance you can get from a particular model size, we have been sort of underestimating it. If you maintain a large enough quality data set, you can actually get a lot more performance from us from even smaller model sizes. Like around that point, we had reached like close to like billions of parameters, like hundreds of billions of parameter models. And Hoffman showed that even with models in like the million or even like the single digit billion parameter ranges, you would be able to get SOTA level performance if you just focused in on maintaining a quality and large data set. Which was at the time like pretty brought about a decent shift in how people approach these problems as well. In addition, he brought about a very practical sort of like observation that you could play around a lot with the learning rate scheduler. So just like a high level intro, learning rate is essentially the step size in typical gradient descent functions that helps you figure out that ideally the global minima point of your objective function. A learning rate scheduler is nothing but something that adjusts how the learning rate changes over time. Typically, you want to start out with a fairly decent sized learning rate because you don't know where the global minima is, and you're hoping, I mean, you typically start out with somewhere around like the max regions of your optimization function, and you want to take large steps so that you move faster towards your global minima. But as you keep on training your model through epochs, you want to reduce the size of that step size so that you don't miss or overshoot the local minima. Like folks who are aware of like gradient descent, and folks who are aware of how like if you increase your step size too large and if you make your step size too small, I mean, like if you increase your step size too large, you might overshoot it. If you make your step size too small, convergence will take a long time, which is why we introduced this concept of learning rate scheduler. And essentially, Hoffman showed that you could be fairly aggressive with how you use your learning rate scheduler, and that could actually also play a decent factor in how the model performance that you achieve with like the smaller models on quality data sets can end up being. So these, I feel, sort of define the space as it is back in 2023, or not define, but maybe provide a mental map of the space as it is in 2023. So n-grams, deep learning, transformer became the state of the art. We saw scaling laws getting applied to transformers, where more model, more data, more compute, all three could lead to better performance. But you couldn't just index on one, you needed to index on 2 to 3 to keep on getting more and more performance, which is why we see this sort of a rat race of everybody trying to get more compute, more data, bigger models, etc. So yeah, hopefully that mental model or mental map of what the space looks like in 2023 resonates with you. And just to maybe call out the big players in 2023, GPT-3 was definitely, like developed by OpenAI, was actually quite a seminal model till that point in time, or pretty much continues to be actually. It was sort of considered SOTA in quite a few tasks. Palm was sort of Google's response. It was a fairly big model, I think around 150 billion or so parameters. And Chinchilla, also from Google. It was actually developed by DeepMind, but DeepMind Google, it's about the same thing. But the idea behind Chinchilla was an idea very similar to LlaMa, that with smaller models, just trained on bigger data sets, quality data sets, you could get better performance. So Chinchilla was along the pretty much same lines as LlaMa, just that LllaMa states that they're trained completely on sort of like publicly available data sets, and Chinchilla may or may not be sort of. There are a few other players as well. Bloom was sort of the community built large language model. It was fairly effective. Similarly, Meta, before they released LllaMa, had like a traditional large language model where they were also indexing on increasing the model size and not really focusing on, oh, we could actually get better performance on our model with a better quality data set. So they initially started with OPT. They also came around like the same route as Google did with Chinchilla. They came to LllaMa in a similar route as well. So yeah, this is the research space thus far. And I'll just check the Excel just to see if there are any burning questions at this particular moment. Like I mentioned, feel free to sort of start dropping questions on the chat. And if you guys have comments, feel free to drop the comments on chat like so many people have already. Just because, like I mentioned, it's supposed to be a casual hangout. The idea is like, as long as we have a group of people, no matter how small it is, as long as we keep asking questions, we'll be able to learn more and more about the space. So yeah, do drop your questions on Drive and any comments you have on chat. The folks who drop questions, I'll be sending out my notes of the LllaMa paper to you all. to those questions to those people who ask questions, just to incentivize you to ask more and more questions. Harish, the paper link was already there as part of the event. You would be able to get it. I don't think I have the link handy, but if you just search LlaMa paper, the early one that was released in Feb 2023, you'll be able to get it. In terms of code, again, so there is this idea of open model and open weights. Just read upon the LLM space a bit more. It's not, the code isn't available like that. Like you could work with the LLM model like by working through Hugging Face or getting the pre-trained model, but I don't think you get the model. I mean, the model code like that, you don't get it. Can you highlight how much adaptive learning rate is used in industry compared to constant learning rate? It's sort of become a standard at this point. It's used almost as often as regularization. I would say like it would be the first thing that you use to sort of figure out if when you plot out your convergence curves, more often than not, they'll be erratic. To smoothen it out, sort of the first things that you do is implement an adaptive learning rate scheduler. If the math gets too technical, actually, we covered that in sort of the guide on how to read papers. You don't need to necessarily. So I guess there are two schools of thought. There is the applied data scientist and there is the research data scientist. So the research data scientist is a set of folks who sort of define what is next in machine learning. So for those folks, yes, understanding the math is quite important. I work primarily as an applied data scientist. So for me, it's more important to understand the intuition behind the method, when to use the method and when not to use the method. So you just need to look at the sort of like whatever we are going to be discussing in that manner, like RMS normalization, which we'll see a bit later on. It's essentially a way to what you do is like when you look at the convergence curves, if you see it's being a bit erratic, or if you when you debug and you see your gradients and you see that there are gradients of very large sizes, which we call exploding, or if you see gradients that are very small sizes, which we call vanishing, then that's a trigger in your head to the fact that maybe you need to apply some kind of normalization to the input values to your deep learning model. So I don't really I mean, I understand RMS normalization is nothing but root mean square normalization. So the math there might not be that hard to comprehend, but I don't really understand why a consistent distribution might help, or I don't really need to understand how the math behind a consistent distribution leads to better or smoother convergence. You don't need to necessarily understand that. You just need to understand more from an applied perspective that, okay, if I see vanishing gradients or exploding gradients, then I need to make sure that when my gradient values are controlled, and by gradient values being controlled, I should use a technique called RMS normalization or some kind of normalization. So just need to understand the intuition behind each of these methods, when to use them, when not to use them, and maybe not all the detailed math, especially if you're in that applied data science space. Yeah, you definitely don't need to understand everything, like especially as a beginner, which is why I'm saying like feel free to ask questions. This is also like so during my master's, one of the best things before COVID, I had the opportunity was like to sit in like a research lab, and like when the PhDs were talking about papers, just I definitely wasn't anywhere close to them, and I couldn't understand everything, but just being in the room, I felt like I was getting introduced to ideas that I normally wouldn't get introduced to unless I had that kind of group. And the idea behind BuildML is to create that kind of group where we just talk about the research or the latest advancements in the field, and we ask questions. That is the only requirement. You don't need to understand. If you don't understand, ask questions. There is no bar to the questions. Whatever questions you have, you should be asking. And that's the idea about the Hangout. And it's also why I introduced sort of an Excel way of asking questions, so that you can feel free to drop whatever questions you want, and nobody's going to be judging you or anything. It's again, the idea is have a casual Hangout. and ask whatever questions you want, and that's how we sort of keep improving. And again, guys, if you have like questions, if you could shift them over to the Excel, that would be awesome, because it helps me keep a track of what questions were asked. Let me know if you can actually access their Excel. If you can't, I can like obviously fix that. But yeah. Yeah, I do see some questions popping up on the Excel, so I'm assuming it's working. I'll take, I think, maybe a few more questions from the chat before continuing on in the interest of time. We can like exceed like 1 hour, so it's okay. Like if you guys have questions, I'll try and answer as many of them as possible. Mm, so we generally use dynamic learning rate. I mean, we use a learning rate scheduler to make it dynamic. That would, again, what you do is you sort of analyze your convergence function, you see how it's going, I mean, like how erratic it is. And if you feel it's too erratic, one way of smoothing it out is the sort of like the learning rate scheduler. There are other ways. But yeah, in papers, quite often you do see, like especially in DL papers, quite often you do see some kind of learning rate scheduler at this point. Share the link again. Not sure which one. If it's for the LlaMa paper, let me just see if I have it handy. Yep, I think this should be the link to the paper. Let me know. Cool. I feel that we understand the problem with 5, maybe say performance to understand how dimensional interaction was same applied to n number of variables. Not sure what I didn't fully understand the comment. If you could elaborate, that'd be awesome. But yeah, feel free to keep commenting, guys. This is typically how the community sort of opens up. Where can we learn the math from base to advanced and apply it eventually, like practices? Introduction to statistical learning in introduction to statistical learning in Python is a really good book. But yeah, feel free to again start dropping your questions on the Excel. I'll stop taking questions off chat. I'll restrict it to the comments, and the questions on the Excel, I'll come back to it at a later point. Okay, moving on with the section. The next part of the phased approach. So like I said, my approach is like Sunday I read through the problem and the solution that a couple of papers are presenting. I maybe pick out 2 or 3 papers. Monday and Tuesday I try and understand the research space a bit better. And again, this understanding the research space, especially if you're sticking to a particular research space, the time taken will actually reduce, primarily because, like for instance, the research that I mostly read is around recommender systems. So for over time, I understand what the benchmark recommender systems really doesn't have a very solid benchmark data set, but sort of like the typical data sets that used in recommender systems are, the typical metrics that are used in recommender systems are, the different ways that they should be breaking down or analyzing a model that they're suggesting for a particular recommendation scenario. So over time, you will start building up this sort of like, again, best way to describe it, sort of this mind palace of knowledge around your field of research. So over time, the time taken for each of these phases will reduce. Now coming to the third phase, understanding the approach and results. So this paper, another reason why I really like this paper, the initial LlaMa paper, is because they talk a lot about how they deal with the data and how they created this data set, and the focus that they gave into ensuring that they are building a quality data set. Like these were some of the, they used quite a few resources for getting public data, but these were some of the resources that where they implemented like very simple techniques to ensure that they have good quality data coming from the source, like from Stack Exchange, removing HTML tags, from GitHub, removing code that is shorter than us. I mean, removing code files that were shorter than a particular line length or a particular number of characters, from Wikipedia, removing hyperlinks. From Gutenberg and books, they removed books that could be duplicates of other books based on how much text was overlapping, etc. So a lot of I would say concern around how the data set is created and how the quality of that data set is maintained. And then they put it through the byte pair encoding algorithm and finally produced like 1.4 trillion tokens. So byte pair encoding algorithm, what is it actually? It's a fairly simple algorithm. Like the idea is to not just consider word as the smallest token, but instead consider subwords. So maybe just to call out the oops, sorry. Maybe just to quickly call out that algorithm. So this is like the notes that I keep creating for each and every paper, and this is the notes that you will get if you I mean, share your questions on the Excel. It sort of is a way of incentivizing everyone to ask more questions. And again, there is no like bar for asking questions. Whatever questions you have, you should be asking them. So the byte pair encoding algorithm is a fairly simple algorithm. Like if you have a word like, let's say, lower, what it does is it breaks down the word to the character level, and whatever characters, group of characters are considered common or occurring very frequently in whatever your corpus is, those are kept together. Like let's say L and O are occurring very frequently, then those are kept together. So it essentially breaks down words to the subword level and sort of creates a new dictionary for you. So in this case, the word lower, based on like what other things were present in the corpus, were broken down into low, S, T, N, E, W, E, R. So these subwords were created. And why exactly subwords? Primarily because I mean, for us it's a bit harder to understand language like this, but for for like a transform model, subword sort of makes understanding language simpler. It helps reduce the corpus in a way, because you're using subwords and not longer words. So yeah, it's a pretty effective algorithm both for training and in terms of like storing a corpus as well. Hopefully that makes it clear. And essentially the 1.4 trillion tokens are nothing but 1.4 trillion subwords like this, that's used to train the model on the next word prediction task. So if low and S was coming as the first and second word, what is the third word? That is the task that the model is being trained on. And the model, if it predicts T correctly, the model is accurate. If it predicts something else, the model is inaccurate, and we go through our typical backpropagation to make it more accurate, essentially. So that's how the training process works. Cool. So that's a high-level overview of the tokenization process. Now, coming to sort of the training process. So the typical training here relies on the transformer architecture. There is an awesome paper about the transformer architecture that I'll just quickly share as well. It's called the Illustrated Transformer. It's actually a pretty, I would say, probably a very popular blog that everybody knows by this point. But I'll just share it just in case like folks don't have it handy. Let me just pull it up. Illustrated Transformer. Yep, just share it on the chat. So do check out this paper in case you don't understand transformer architecture. But yeah, maybe in the interest of time, I'll skip over the transformer architecture. The basic ideas are like the attention model, and sort of like yeah, the basic or the core idea that you need to walk away is attention. And attention basically is one way of going about predicting the next word by giving importance to all the words that came before. On a high level, you just need to maybe take away that fact that the transformer architecture is a deep learning model which tries to predict the next word by giving sort of a configurable weight to the words that it has seen before. At least in the context of next word prediction, that's basically how a transformer model tries to learn patterns. So they had the initial transformer architecture, which is sort of I guess developed in 2017, and they made some improvements on the transformer architecture, each based on other LLMs. So one thing that they did was they pre-normalized the input of each transformer using RMS norm, that's root mean square normalization. So let me maybe just pull up the transformer model quickly. Yep. So the transform model, within transformer, there are these things called encoders and decoders. You don't need to necessarily I mean, you do need to understand it at some point in time, but for this session, we can abstract it out if in case you don't understand it. But the idea is there are these deep learning layers within the encoder, and what we are doing, or what they saw, was that when they were training the model, they essentially saw vanishing and exploding gradients, and to sort of control for those vanishing and exploding gradients, they wanted to normalize the input that was being fed into each of those layers. And the RMS norm was sort of um, used before each layer. And what RMS norm does, it's nothing but, let's say X is the input that's going to be provided to a layer. It calculates the root mean square of all the X values. So essentially squaring all the values, taking the sum, and taking the average, and then taking the square root of that average, and using that as the denominator to divide each of these X values. The idea essentially is that you want to have a distribution that has a consistent mean and standard deviation. So this way, you won't have values that are very huge, and you won't have values that are very small. Primarily because if you have values that are very huge and values that are very small, like I mentioned, it leads to these things of vanishing or exploding gradient. Essentially, the values in vanishing gradient, it becomes close to zero, which means that your model won't learn anymore. And exploding gradients, value becomes infinite, which will lead to sort of this your model will essentially error out at that point. So to avoid that, they're essentially normalizing these input, and RMS norm is just one way of doing the normalization. There are plenty of other ways. Why exactly they are using RMS norm? It's because it was used in the Palm model. This is why I mentioned it's sort of important to understand the research space and see if the paper that you're reading builds on the previous research. So they're building on the Palm model that is developed by Google, where they found that RMS norm was one of the most effective normalization techniques. Similarly, the activation function, they're replacing ReLU with SWIGLU, and that again comes from, I believe, sorry, the RMS norm is used in GPT-3, not Palm. The SWIGLU is used in the Palm model. So SWIGLU again is, so ReLU, as everyone knows, it's like a simple activation function. The idea is like positive values are shown as is, and negative values are sort of made to be zero. And since the function is constructed in that way, it's not differentiable at the 0 point. So that's essentially what ReLU function is. SWIGLU essentially has two advantages over ReLU. One, it's differentiable at every point, and the only thing that you need to take away from that, or the only thing that I ever took away from that, is that differentiable functions essentially mean better convergence, smoother convergence. So SWIGLU essentially is differentiable at all points, and therefore gives way to smoother convergence. And another thing is, SWIGLU has this sort of element-wise multiplication of the values with a swish function. Swish function is nothing but, you can think of it as a very similar to sigmoid. The only thing you need to take away from swish function or the SWIGLU function is that it has a gate. It's a gate. It has a gate which controls how much of your input should go into the next layer or not, and it does it in a very differentiable way. So irrespective of whether the input is negative or positive, it uses sort of a gating mechanism to figure out how much input should flow further. That's the only I would say intuition you need to derive from the fact that a paper is using SWIGLU. Similarly, they are using rotary positional embeddings. So positional embeddings in the context of next word prediction tasks. Again, it was brought out in the attention is all you need, the initial paper that introduced the transformer architecture. So what they used positional embeddings for is to showcase where exactly that token is sort of located within a particular sentence. So rotary positional embeddings is a slight advancement on that. primarily taking into consideration not just the absolute position, like from the start of the sentence where it's located, and not just that, but it also takes into consideration the relative position of how the embedding for one particular word is located with respect to others as well. And again, rotary position embeddings was something that was implemented in GPT Neo. It was another model, again, a smaller version of GPT that, again, OpenAI sort of came out with. So again, this paper is sort of building on prior work, which is a very good sign. So yeah, let me just maybe take a quick pause here, primarily because this is sort of the densest part maybe of the paper, and typically people have quite a few questions. So again, feel free to drop your questions and we can take it from there. Yep, yep. The transform and explain visualization will also help. Yeah, that's a really good call out, Krishna. Thank you. Maybe just a quick review of any other comments. How are the upcoming small language model training parameters different from large man? Apart from using lower number of training parameters, do they use and a set of hyperparameters which specifically for SLMs and not exactly for LMs? SLMs are you don't need to necessarily confuse it with LLMs. It's not actually even like the same approach, I would say, or the same utility, I would say. Yeah, it's not just about using a different number of parameters. The fact is they borrow a lot from what LLMs have achieved in a sense. So they're not starting from the same starting point. So so in maybe training there is this idea of teacher forcing. So you can maybe look at SLMs as sort of that way of the fact that they're learning from what LLMs have learned thus far. The idea is like, in most deep learning models, when you actually inspect the parameter values, you'll see a lot of them have values like very close to zero or very negligible values. So there have been techniques that have been out there like quantization and stuff like weight dropping, where you essentially try to reduce the size of your large language model. The problem is once you reduce it beyond a particular point, you do see quite heavy loss in performance. So SLMs essentially they borrow all the learning that LLMs have. So they're not actually starting from the same point as LLM. So you can't really compare them maybe like 1:1. So yeah, maybe that gives a rough idea. It's more about how they're trained, less about the techniques that are necessarily used in them. Yeah, books. Yeah, if you're looking for the math behind machine learning, definitely. I also feel like the books are fairly effective. There are quite a few good books, but I also feel like certain people are visual learners, and YouTube does play. I mean, coming to does have its own utility. So wouldn't like write off YouTube as such. There are quite a few YouTubers who I like as well. If you need like suggestions, feel free to DM me on top mate and I can provide you one. Can anyone share the drive link again? I don't think I gave a drive link. Maybe the Excel sheet link. I'll just post that in chat again. Oh, awesome. I think that somebody already did. Cool. So yeah, kind of knowledge distillation. Yeah, exactly. Kind of knowledge distillation. Yeah, thank you. I'd sort of forgotten that word. Yeah, knowledge distillation in a way. Yeah. Cool. I hopefully, like, again, I understand that this area is a bit dense, and maybe definitely it could have like flown over the head of a lot of people. But I do encourage you guys to sort of again ask questions around it. That's the best way to learn. There is no bar for the questions. The idea of this group is just to have a casual hangout. So again, guys, feel free to ask questions. Like drop your questions on the Excel. Cool. And in terms of like optimization, just the architecture is often not enough. So they do use a lot of I mean, slightly different techniques, I guess. The cosine learning rate scheduler is a kind of an aggressive learning rate adaptation mechanism, where by the end of like a few runs, your learning rate will be maybe like 10% of how it started out initially. So it's just a way of decreasing your step size. Essentially, you just need to understand that as the new intuition. Your learning rate is your step size. Cosine learning rate is a way of decreasing the step size. Adam W. Adam, I'm hoping a lot of folks are familiar with. It's a common way of finding sort of the minima and optimization algorithm. Adam W is nothing but within Adam, there are these parameters that are used for weight decay. The problem with the regular Adam is that those parameters are sort of implicitly built into it. Adam W has a slight advantage that it separates the weight decay from sort of the rest of the optimization. So essentially, it's taking out a small regularization component from the optimization problem, so that the optimization problem, so that you can essentially control better how much regularization you want to introduce here, and it's able to achieve better convergence in a sense. Similarly, they do use a lot of other techniques like weight decay. Weight decays, since they're using Adam W, they're adding like additional regularization. Like weight decay, you can consider it sort of very similar to L2 L2 regularization. Gradient clipping, again, like I mentioned, there is this phenomenon of exploding gradients where your gradient values reach up to infinity. Like for folks who have worked on deep learning, like if you inspect your gradient values, you'll see like some gradients are becoming too big. So gradient clipping is nothing but a way of like, okay, the gradient values shouldn't go above this. You set a specific value, and ideally it should never go above this. And then they use warm-up sets. Warm-up steps are, especially in large deep learning models, it's just a way of, especially when you're starting out from randomly initialized values in your deep learning model, you sort of use warm-up sets with a specific learning rate, because during those in initial sort of runs, the model's convergence can be very hazy, or sorry, not hazy, very erratic, I guess. So it'll be a bit all over the place, and the idea is these warm-up sets sort of help you create a bit more stable convergence function down the line. It's something that's again, especially I mean, like personally, I haven't ever used it because I've never worked on models that large. But folks do say that when you reach to a certain point where the models have like quite a huge number of parameters, like here we're talking about billions of parameters, warm-up sets do help. Cool. I'll take a quick pause and then just check in on any sort of questions that we have on the Excel. Good quality data implies better pre-processing techniques. Yes, they do ensure that the text quality within the data set is yeah, essentially quality text, that they're trying to remove any text that may not be representative of the domain that they're looking for. Like within GitHub, they're looking for basic line, like so that they're essentially trying to model it on quality code. Or on Stack Exchange, they're trying to get the actual questions and the answers. So they're removing all the HTML tags because it's not relevant to the domain that they're trying to represent, which is question answering. So yeah, basic pre-processing techniques to make sure the data represents the domain that they want to model. Where can we learn the math? Yeah, Introduction to Statistical Learning in Python is a good book. Deep Learning by Ian Goodfellow is another good book. How much adaptive learning rate, like I mentioned, there are quite a few functions, quite a few ways to smoothen out convergence. Adaptive learning rate is one such way. SLMs we already covered. What does parameters mean, as well as models, and why can parameters reach over 1 billion? So models are nothing but models are nothing but you could say a mathematical function, and the parameters are what can be learned about that function. For instance, if you have a function ax plus by equal to c, and x or ax plus b equal to y, what you're trying to do is, using your input value x, you're trying to predict what y will be. For instance, let's say based on what the humidity, like the humidity today is, you're trying to predict if there's going to be rain or not. So humidity would be variable X, rainfall yes or no would be variable Y. So what you're trying to do is you're trying to predict, build a model which uh, inputs what the humidity level is today and outputs whether there's going to be rainfall or not. So let's say the model is as simple as A into humidity value plus B, a constant, some kind of constant to represent some base probability that there will always be rainfall. So A into humidity level plus 10% chance there is rainfall equal to probability of rainfall today. So that is that model, the ax plus b, that is what we call a model, and in this case it's called a linear model. We make an assumption that you can use a linear model to predict the probability of rainfall, and the parameters are nothing but a and b. The things that you can learn or you can adjust in that model is sort of the parameters. So now why does parameters reach to up to 1 billion? So the task that we are trying to perform our best on is nothing but the next word prediction task. So what comes next? What comes next? And not just maybe the next word, maybe the next set of few words, or once you predict the next word, you want to use that to predict the next word, to use that to predict the next word. So it's a somewhat complicated task, which can, like predicting the next word can have sort of, I wouldn't say an infinite set of probabilities, but um, quite a large number of probabilities in what the next word could be. It may not, it may seem it may seem obvious to us because we have a lot of world knowledge about how people communicate and how grammar works, but to a mathematical model that doesn't understand a lot of that world knowledge, that common sense, that basic math, all of that the model doesn't understand, to it predicting the next word is quite a complicated task. So with the billions of parameters, what we are trying to build into it is a certain sense of common sense, a certain idea about how math is, a certain idea about how not to be maybe like toxic or biased. So we're trying to teach all of it using these billions of parameters, and based on that knowledge, it's trying to predict the next word. Um, to a certain extent, like this is a very high level explanation, and maybe uh, even like a kind of incorrect representation, because there are a lot of people who do claim that these large language models do not understand and they are just nothing but next word probability predictors, and they don't really model anything like common sense reasoning or model algebraic knowledge or even understand toxicity and bias, that they that these parameters are nothing but predicting the probability of the next word. But yeah, different schools of thought. But to understand, I think it's better, especially if you're new to the field, just understand that these parameters represent different elements of human thinking that may seem obvious to us, which like common sense, like mathematical reasoning, like toxicity, like bias, stuff like that, that seem obvious to us. It's sort of representing that in the parameters. I'm looking for resources that help me in building applications using LLM. I find your model for specific tasks. Struggling with other limitations like GPU and cloud. Any other suggestions on resources that can help? So yeah, there's a pretty cool YouTuber that I follow. Actually, there are a few. Um, uh, on LinkedIn, there is a content creator called Aishwarya Naresh. I think she's a good content creator to follow. Let me just maybe see if I have. Yep, I think I have her. Yep. This is her GitHub. This is a good place to start with understanding LLMs, learning about LLMs, and a lot of free resources around building LLMs. There is also a very good content creator on YouTube. I think his name is Krish. Yep, Krish Nayak. He's a really good content creator on YouTube who builds a lot of these Gen AI tools, including like I mean, even going a step further into like the engineering aspects of I guess using LangChain, LangIndex, sorry, LlaMa index, LangGraph, a lot of the, I would say, what's considered the latest trending tech in Gen AI. He does use it and he builds a lot of solutions around it. So check his channel out. He explains things in a very good way as well. So yeah, these might help. Cool. I think in the interest of time, I'll go to the next section, which is the training section. So yeah, efficient implementation. So like I mentioned, um, because of the size of these models, how they approach training is sort of very nuanced, and they build again on top of the prior work in the field. So in this section, again, they have like certain sort of modifications that they have taken based again on prior work that we have seen in the field. So in transformers, there is this concept of multi-head attention. They use a different variation called causal multi-head attention. So again, in an intuitive manner, the basic idea is if you have next word prediction, the idea is only the words that you have seen before matter to next word prediction task, right? So in the context of LLMs, that means you only need to focus on the words that came before. And that's what causal multi-head attention basically means. In regular attention, what they do is they don't really use next word prediction. They have this task of masked token prediction. Essentially, within a sentence, they hide one word, a word that could be anywhere in the sentence from the model, and they have the model predict that word. So how they predict that word is they could use the words from before the masked word, and they could use the words after the masked word. So in typical attention, you use words from before and after. But in causal multi-head attention, because the task is next word prediction, you only use the words that are before. So yeah, it essentially helps to reduce the amount of stuff that you store, and it also helps reduce the runtime. Another thing that they use is they have their own implementation of backward pass and not use the PyTorch's inbuilt backward pass, primarily because PyTorch's inbuilt backward pass has this. So PyTorch is built as a framework, and the key idea behind the framework is it has to be flexible. So it does a lot of things in a repeated manner that could be avoided if you know what your architecture looks like. If you are fixed about your architecture, there are a lot of ways to improve the performance, and they're essentially leveraging that where since they know what their architecture looks like, they're able to do slightly better than what PyTorch offers out of the box. Basically, that's the only thing that we need to take away. And they also leverage a couple of other things like model and sequence parallelism. Again, most of it's covered in the notes, and everything I mean, everybody who's asked questions will sort of get the notes as well. Probably like since this is the first session, and I definitely have room to improve in terms of like managing time and encouraging discussion, I'll actually just release the notes to everyone for just this session. But yeah, keep asking the questions that you're already asking on the Excel. That's a good way of encouraging discussion. I'll just move on to the next slide. Yeah, in terms of like results, they to try and establish this sort of SOTA, they primarily worked on two types of tasks: zero shot learning and a few shot learning. Zero shot learning is they've trained the model and they just essentially give a textual description of what they want the model to do, and they see what answers the model produces. They evaluate it on two types of formats. One is like they just ask the model to generate the answer, and which is called open-ended generation. And then they do another kind of task where they give the model, okay, these are the answers, these 5 choices, the answer is within these 5 choices, pick which one you think is the best. So that's one way, that's another way of sort of evaluating zero shot learning. Similarly, they evaluate on few shot learning. Few shot learning, they provide a few examples of what the task is and how it would be solved, like around less than 64 in like for the model to understand one particular task. And they ask the model to generate answers, or similar to like the MCQ, they rank the options. So they tested it on a bunch of these benchmarks, again covered a bit more in detail on the notes, which I'll send out pretty soon. So yeah, they're essentially assessing for common sense reasoning, closed book question answering, reading comprehensions, mathematical reasoning, code generation, massive multitask language understanding. These sort of 6 tasks. There were a few more, but I think these are the most crucial ones, especially common sense reasoning, mathematical reasoning, and MMLU. These four have continued to sort of remain as aspects of evaluation that every LLM is being assessed on. The benchmark data set keeps on evolving and updating, but this idea of that, okay, the model should be tested for common sense. The model should be tested for its ability to do math. The model should be tested for the MMLU is nothing but knowledge on a lot of fields like STEM fields, business, etc. Essentially, sort of a variation of closed book question answering. So evaluating the model on these 3 tasks have sort of become a standard even now, like even in 2024. If you look at the like one of the sort of like leaderboards that's fairly popular is the Hugging Face leaderboard. I'll just link it on chat. But even in that, you can see like MMLU is still around, math is still around. So this is also a good takeaway. And from a paper perspective, I like that. I like the fact that they're using data sets that are considered sort of benchmark, and they're using metrics that are considered benchmark. Like in most of them, the metric is like accuracy. In some, there is this metric called exact match. Again, like pretty simple to understand. It's there in the notes as well as on the paper also. It's actually pretty simple to take away. Cool. Coming to the last section of how do you critically analyze the paper. So like I mentioned, what we want to first check is based on their approach and the results that they're presented, are they evaluating their approach in a standardized benchmark sort of driven manner? Essentially, are the data sets and metrics benchmark? In this paper for 2023, yes, they were using mostly benchmark data sets. When comparing to like the GPT paper, the Palm paper, and a few of the other papers, there were other aspects those models were sort of evaluating their LLMs on, and like LlaMa also evaluates its model on a few additional aspects as well. Like I like their focus on toxicity and bias and truthfulness. They had like few data sets around that, and they showed that their model does have certain level of toxicity. Their model is biased in certain ways, and the model is not very truthful. Like it's not able to identify what is fact and what is fiction. Actually, no model currently does that well in the truthfulness category. But I like the idea that this paper sort of used a lot of benchmark data sets and benchmark evaluation metrics, and most importantly, analyzed their model from multiple angles. So this is a very good indication of a good paper, at least in my opinion. And yeah, the current benchmark data sets you guys will be able to see on Hugging Face. I've already dropped the link on chat. One of the drawbacks I feel of the paper is that in certain cases, LlaMa doesn't do as well as the other models, but they don't explain why it doesn't. And I do see that as somewhat a trend in this space, where they're not explaining a lot about why they feel the model is doing certain things, or the model is not achieving certain SOTA level performance in certain categories, and it is achieving SOTA level performance in other categories. So that's an interesting area, and I think it's maybe a good area for us to keep an eye on. If a paper comes out that actually starts explaining a lot of these concepts, I think that would be a pretty, I mean, and especially if they're able to explain it in a verifiable manner, that would be a pretty seminal paper, and it's probably a paper to look out for in the space. And yeah, like I mentioned, these different aspects of how the paper analyzed, I think that's a good trend, and I do see that continuing, and I feel like it's something that we should add to our mental map. That okay, as I'm moving in this LLM space, I should probably assess my LLM not just in one niche. I mean, it depends upon your use case. If you're going for a niche use case where you're fine-tuning the model, then it's absolutely fine. But if you're just working in LLM space, I should probably analyze my LLM from more than one angle, like math, MMLU, toxicity, bias, truthfulness. These are the 5 different angles I should be analyzing my model from. And that's something that we should probably add to our mental maps when we read future papers in LLMs or we do any future work in LLMs. Cool. Finally, let's do a quick Q&A. Before that, just wanted to do a quick shout out to one of the sort of like um, solutions slash one of the products that sort of is supporting a lot of the BuildML efforts as well in a way. So quick shout out to Automate Apply. Primarily, it's a tool that sort of helps reduce a lot of your job hunt process. For me personally, I had like I did use one of these services when I was doing my masters for about a month. Primarily, I was in it was 2020. We had sort of like start of COVID. We had some of our offers get rescinded, so I needed to land another offer pretty fast. So I'd use one of these services, not specifically Automate Apply, but another one at that time. And Automate Apply is quite a bit better, primarily because of the pricing. It's like half as cheap, like yeah, 50% lower than the ones that I used. And primarily what it does is it automates the job application portion for you. So like probably the worst aspect of job applications is the sort of the 1 to 1.5 hours that you have to spend going through different job boards, finding a job that fits for you, and then applying. And it's not just the 1.5 hours you spend on job applications, it's how drained you feel after that, and sort of how despondent you feel after the fact that you have applied to so many places, you don't get a response back, and it's so much wasted time because it doesn't necessarily build any valid skills. So Automate Apply is like a good solution to sort of outsource that out. It's like $1 for 2 applications, so pretty cheap. So do check it out. I'll drop the link in the chat as well for folks who are interested. So yeah, quick shout out to Automate Apply. And yeah, now we can just quickly go into the discussion part of the section. Yeah, and just a quick call out to BuildML. So BuildML is sort of this community that we're trying to build. As part of the community, we do have these weekly research hangouts. Again, supposed to be fairly casual. We'll just have conversations about maybe one paper that we read and questions around that particular domain. We BuildML will also be working on building out monthly sort of like projects. We'll be launching on October with recommended systems related projects. And we'll also be launching study groups starting November, so that as data scientists, we can make sure that our foundational skills are good. Primarily, BuildML started out with this idea that our end goal shouldn't just be landing a job in data science. Our end goal should be building a career as a data scientist. And how we actually support that is by making sure that we continuously build products that are relevant to what's latest in the field. We brush up on our foundational skills, for which we will have study groups, and we keep reading or exposing ourselves to research in one way, shape, or form. That's why we have the weekly research hangouts. So yeah, all of it's like pretty casual, and it's a free community for you guys to join. Do follow us on LinkedIn. I'll quickly drop the link as well. And yeah, quickly moving on to these questions. Oops. I think we got until models and parameters. I'm looking for resources. Yep. What's the difference between the relation and rotary positional embeddings, or are they the same? No, rotary positional embeddings are relative to one another. So there's positional embeddings and there's rotary positional embeddings. Rotary positional embeddings. Positional embeddings essentially indicate the position in the sentence. Rotary positional embeddings also have a relative component to it, which makes it a bit more representative of representative of where they're located in a way. There's more details in the notes, which I'll be sending out, but the high level intuition is sort of that. How is research helpful in the day-to-day job, and how can we improve these abilities further? In terms of like day-to-day job, so it really depends. Like when you get a business problem, typically what you do is, A, you validate that the business problem really needs to be solved. B, you ensure that machine learning is what is required to solve it or not. And how you do this is you build a no ML solution, and see if that actually fixes the business problem, or you recommend a no ML solution that somebody else builds and see if it's fixes the business problem. And if it doesn't, you build a basic ML model and see if it improves upon the no ML solution. That's when you sort of realize that, okay, ML should be applied. Then you sort of start with a simple ML model. Typically, in industry, like a go-to nowadays, I mean, it used to be linear regression or like logistic regression. Nowadays, it's more of like XGBoost. But yeah, you build out like a simple ML model, and you try and see the value it adds to business with that simple ML model. If the value added is quite significant, and if business says that yes, we are interested in improving the performance of the model, we can give you a bandwidth of maybe a month or two, I mean development time, and we'll be sort of like willing to invest in that. That's when you sort of go about and read papers and figure out, okay, what are the best models that within over the next 1-2 months I can experiment with and figure out how to best solve this problem. So that's when reading papers come into play. More often in industry, very few, I would say, like it follows the 80-20 rule. Like 80% of the projects you would be able to solve with like basic ML models. Very only like 20% of the times would you actually need to dive deep into research and build models. But again, the idea is you need to be ready for that. It's this example that I often give, like research, you need to be able to understand, comprehend, and implement research, because that is a key component of your role as a data scientist. It doesn't matter whether it's used less often than the others, but it is a key component. Um, for instance, when like during air hostess training, there the training involves a lot of emergency scenarios, landing on water, first aid, all of those things, and that's because that is sort of like their primary critical role, to take care of passengers in case something goes wrong. It's not just about like inviting them on and making sure they have a comfortable journey. So similarly, as data scientists, you need to understand how to do research, how to implement research, and how to build out ML projects. It's a critical part of your role, which is why I encourage people to, even if you don't read research, sort of absorb research in one way, shape, or form. How is okay? I've been working on LLMs for a while, just application oriented to evaluate. Applied LLMs, I generally use Blue, Rouge. Do you have any other recommendations if you don't have labeled data? I'm wondering what task you're evaluating the LLMs on. If you could go into a bit more detail, that would be good. But typically, there are benchmark data sets for most tasks at this point. Um, if you're like fine-tuning a model on something specific, then yeah, Blue and Rouge are good ways to go about it. Yeah, Blue and Rouge are pretty decent ways to go about it. While reading a paper, I came across a concept which I don't understand. Would you suggest holding off on the rest of the paper and reading about the concept first and coming back to the paper, or would you suggest going ahead with the paper? It depends upon how critical that concept is to that particular paper. If it's something about something novel that that paper is doing, then yes, stop and try and understand it. If it's some specific technique, like for instance, rotary positional embeddings, this was something new to me as well. When I was reading the paper, I didn't fully understand it. I just kept on reading. I tagged it, and I made a note that okay, I should probably go back to it afterwards. And I made like some notes about rotary positional embeddings afterwards. But when I was reading the paper, I didn't fully understand it as well. I just kept going. Can you tell a bit about the strawberry problem? Seeing them a lot in Twitter these days. I'm not aware what the strawberry problem is. If you could explain, that would be helpful. I'm sorry. Yeah. What are the different ways to evaluate gradients? I know about them, attaching the hooks and evaluating them. That would sort of be the best way, I guess, to evaluate gradients. Yeah. Was there any specific, I guess, any drawback that you found thus far, or just to understand, like what what are you trying to solve for, maybe, or what isn't this covering, maybe. How is causal multi-head differential from multi-attention mechanism? So yeah, causal multi-attention. So multi-attention so multi-head attention is nothing but using multiple heads of attention. Attention is nothing but using the weights from words before it and words after. So typical attention is for masked token prediction problem. So you can use attention from, or you use words from before the mask token, and you use words from after the mask token to sort of calculate the attention weights, the key value pairs to predict this mask token. But in next word, just for next word prediction, you can use causal multi-head attention, which is nothing but I will only use the words before the word that I want to predict. That's the only sort of difference. Hopefully that comes across clear. It's just for next sentence, I'm sorry, next word prediction tasks where you have that strict left to right ordering. Otherwise, like as you know, attention sort of brings in the embedding from all the words around the mass language token. Is there a way to connect one to end for 10 minutes? Yeah, you can just drop a note on topmate. My topmate is maybe, let me just quickly comment my topmate. This would be my topmate. Feel free to grab a slot. How do different learning rates impact the performance models in practice, and how do you decide which to use, when to use adaptive learning rates or constant learning rates? So yeah, learning rates is nothing but the step size. If you have a very large step size, your convergence will take a long time. If you have very small, sorry, if you have a very small step size, your convergence will take a long time. If you have a large step size, your model won't converge no matter how long you train it. Adaptive learning rates are used when you look at the convergence pattern. If you see it's too erratic, then that's when, like, essentially you after very many, I mean, like maybe like 10, I mean, after a set of epochs, you'll be printing out your loss function, right? If you see the loss function continuously decreasing, that's good. That means your problem is converging. But if your loss function is like all over the place, that means your model isn't converging smoothly. One of the techniques you can use at that time is an adaptive learning rate scheduler. You have other techniques you can use as well, but some people do like using adaptive learning rate schedulers at that point. What is the best way for a second year undergrad like me who's eager to break into the field to reach out to you for guidance and help? Yeah, feel free to reach out to me on Topmate. I mean, I provide free guidance. Everything on BuildML, all the sessions that I lead will continue to be free. There is like some other content on there as well, but all the content that sort of like all the sessions that I lead will be absolutely free. Yeah. So just feel free to reach out to me on my Topmate. Good. I think that's about all the questions. I'll definitely send out the notes to all the folks who dropped the questions, as well as everybody who was on call, just because it was the first session and I feel like there is definitely room for me to improve on how we sort of do these sessions. But again, the idea is casual hangouts. Every weekend we go over one paper, maybe learn something new, ask some questions. There is no bar for the questions. Feel free to ask whatever questions you want, and if I know the answer, I'll definitely help them. Strawberry problem, like I mentioned, I'll follow up on that, and I'll try and answer that question. Wasn't aware of that term. And I think I didn't properly explain rotary position embeddings as well. I did make notes about it, but for some reason I can't remember how I understood it right now. I'll follow up on that as well. But yeah, hopefully folks had like a decent, I mean, got a decent understanding or a mental map of LLMs as it was in 2023. We'll definitely keep reading more papers. Next week, probably a paper more around recommender systems, but we will definitely have more papers around LLMs just because it's such a trending / useful topic at this moment. But yeah, thanks everyone. Thanks so much for your time. Feel free to drop any questions, additional questions you have on Topmate. Do check out BuildML. If you guys can support us on Instagram and YouTube, that would be amazing. We'll be launching pretty soon in the next month or so, where we would again push out educational content all for free. The idea is to create a community. There is strength in numbers. So if you guys can support us, that would be really impactful. Awesome. Thank you guys. Thank you so much for your time.